Okay, in this example, we have a car which is traveling to the right with some initial speed of V naught. The car has a bumper in front. The bumper is attached to the car with two identical springs, each spring having a stiffness of K. And then when the bumper hits the wall, it sticks. And what we want to do is find out, knowing the maximum compression that we have for the springs, what is the stiffness of each one of those springs. So we're looking at the relationship of a change in speed to a change in position. That's very typical of the work energy equation. Free body diagram here, pretty basic. In fact, I'm going to draw the free body diagram of this thing from the top. And if we look at that from the top, we have, as it says here, we got two identical springs. The springs have the same stiffness. They will have the same compression. So we basically have identical spring forces that are acting on it. In terms of work, we don't need to find the work due to those, because we're going to put that in V, the place where you should almost always put the work due to springs. So in the work energy equation, we have T1, the initial kinetic energy, is 1/2 mv naught squared. The initial potential, well, there's no change in gravitational potential. The car is moving along a horizontal road. The springs initially are uncompressed, so V1 is a 0. T2, in general, that's going to be 1/2 mv squared. But since we're looking at maximum compression, the speed at position 2 will be a 0, therefore the kinetic energy is a 0. And V2, for each spring we have a positive 1/2 K delta squared. Okay, and we got two of those springs. Both springs again have the same stiffness K. They're going to be compressed the same, so we just multiply that by 2. Since there's no dissipation in the model that we have here, therefore the only forces doing work are the spring. We're putting that in V, so there's no non-conservative work. The work energy equation, T plus V plus the work at position 1 is equal to T plus V at position 2, 1/2 mv squared. The initial potential is 0. We said there's no work being done, which we're going to put in U. The final kinetic energy, or the kinetic energy at position 2, is a 0, because we're looking at maximum compression. And V2, therefore, is just K delta squared, like that. So from this, we can find the stiffness in each spring K by taking mv naught squared, dividing that by 2 delta squared. So that is the stiffness that's required in those springs to give that maximum compression of delta. So again, a very basic application of the work energy equation. Since the only forces acting on the car during the impact, they're doing work, we're not taking into account any air resistance or any dissipation in the bumper. So energy is conserved. T plus V is a constant. It starts out with 1/2 mv squared. Is in energy, it ends up with twice the 1/2 K delta squared, and from that we solve for K.